Our final lesson in Topic 2 is 2.7, Linear Quadratic Systems. In this lesson, we'll graph these kinds of systems and find their points of intersection and verify our results. We'll also look at graphing systems of inequalities. A linear quadratic system is going to be two or more equations that have linear functions and quadratics. To graph them, the first thing you're going to want to do is just graph each equation separately. You're going to want to take your time and graph all the way to the edges of your coordinate system. Then you're going to want to look for points of intersection. Do the graphs intersect at all? There we go. If you find them, notice in the directions it says to verify your results. Verifying is easy. You just have to plug them back into both equations. Now, we did that back in Topic 1. However, a lot of students omitted that from their final results on their topic test. Make sure that if you're asked to verify, you do this last step. Example 1a, solve the system graphically and verify. Notice we have a quadratic, y equals x squared, so we're going to have to recall how to graph that. And we have y equals 2x, there's our linear. We have to graph both of them. Let's start with y equals x squared. Now that's the parent function for a quadratic. Hopefully you remember that the vertex is at 0, 0. If you plug in 0 for x, 0 squared is 0. Now if you go 1 to the right, 1 squared is 1. If you go 1 to the left, so on the other side, negative 1 squared is also 1. If I plot those 2 points, I'm on the right-hand side and the left-hand side. If I count 2 to the right, 2 squared is 4. And if I count 2 to the left, negative 2 squared is also 4. This is just review from graphing parent functions for quadratics. 2 to the right, up 4 on the right-hand side. 2 to the left, up 4 on that left-hand side. Go ahead and draw a curve through those points, and that would be the parabola for your quadratic function. And hopefully your sketch looks something like I have on the right-hand side. Now the linear should be a little bit easier. If it's y equals 2x, that means the slope is 2 over 1, and the y-intercept is 0, 0. So what I'm going to do is I'm going to plot 0, 0, and then count up to 1 to the right, up to 1 to the right, and continue that pattern all the way to the edge. Then I'm going to count down to 1 to the left, and so on, just in the opposite direction. Go ahead and connect a line through those 2 points. Actually, it's through all of the points that we graphed, and you should get a graph similar to what I have on the right again. Step 1, graph them separately. Step 2, you're looking to try to find points of intersection. Well, I notice they intersect right at the center at 0, 0. And they also intersect up here, it looks like, at 2, 4. That's what we are going to kind of predict our points of intersection to be. Step 3 is to verify those results. We're going to test 0, 0 in both equations and test 2, 4. You have to test both of them. If I plug in 0, 0 into the first equation, does 0 equal 0 squared? It's kind of a silly question to ask. Yes, it does. If I plug that into the second equation, does 0 equal 2 times 0? Yep, that works as well. We verified that both of those points, 0, 0 is on both of those lines, so that's a solution. Now do the same thing with 2, 4. Plug it into that first equation. Is 4 equal to 2 squared? Yep, that's true. And then our last one is 4 equal to 2 times 2. Yep, that's also true. So that's your verify to show that your solutions are 0, 0 and 2, 4. Let's try another example. Solve the system graphically and verify your results. We have a quadratic and we have a linear. I want you to graph each function. You can make a table or you can use transformations. Graph each function separately, then press play, and we'll go from there. Hopefully you took the time to graph both of those separately. I noticed with my quadratic function that it was just the parent function translated up 2 units. So I moved my vertex up to 0, 2, and then I plotted my points similar to the ones that were in the example up above. My linear part of the function, or the system, my slope is -1/3, but the y-intercept is 1. As I graphed that line, I noticed connecting them, I didn't get a point of intersection. So if there are no points in common, we say that there is no solution to the system. When asked to solve a linear quadratic system that doesn't include graphing, we just have a few steps to follow. The first thing you want to do is get y by itself in each equation. When you do that, what you'll do is you'll set the 2 equations equal to each other, even though one's linear and one's quadratic. So we'll set equal to each other, and solve for x. You may get 0 answers, you may get 1 answer, you might get 2 answers. However many answers you get for x, you'll have to go back then and solve for y. When you're done, you should have ordered pairs, so write your solutions in ordered pair form. Let's see those steps in action for example 1c on the right. Solve the system. We have y equals 3x squared plus 3x minus 5. There's your quadratic. And then 2x minus y equals 3. There's the linear. Now taking a look at step 1, we want to get y alone in each equation. Well, that first one, y is already by itself, so that's good. In the second one, take 2x minus y equals 3 and get y by itself. Now what I would do on this one is just move y over to make it positive, and that gives me 2x equals y plus 3, and then subtract 3 to the other side. And you get y equals 2x minus 3. Wow, I'm not sure where I was going with that. Hang on. Sorry. 2x minus 3. There we go. So in both equations, y is isolated. Step 2, we'll set the equations then equal to each other. In that first equation, we have y is equal to 3x squared plus 3x minus 5. And in the second equation, y is equal to 2x minus 3. Therefore, 3x squared plus 3x minus 5 should be equivalent, oddly enough, to 2x minus 3. If we can solve this for x, we'll have part of our solution. Now remember, anything with quadratics, we always have to set it equal to a key value, and that key value is 0. That means I'm going to move 2x over by subtracting, and I'm going to add 3 to my constant. That's a 3 right there. There we go. That gives us 3x squared plus x minus 2, and then on the right-hand side, we have 0. To solve a quadratic, we now know we have lots of options. We can factor, we could complete the square, or we could do quadratic formula. Recognizing that 3 and -2, I think we could try to factor this one. It's a little faster than quadratic formula, but it may or may not work. So if it doesn't work, we might have to default to quadratic formula anyway. Let's give it a shot. I'm going to take A times C. 3 times -2 is -6. And then let's split it to get B. If we want to get positive 1 in the middle, I know we could do 1 and 6 or 2 and 3. I don't think 1 and 6 are going to work at all. For 2 and 3, I would need to make the 2 negative and the 3 positive. And that should give us positive 1. Let's split the bx in the middle. We have 3x squared minus 2x plus 3x. And that's the same as plus 1x up above. And then minus 2. Now we want to group this, so I'm going to put parentheses around the first two and the last two. In 3x squared minus 2x, the only thing they have in common is an x. And then we'd have 3x minus 2 left over. Now in the other parenthesis, we already have 3x minus 2. Nothing factors out of it, so we need a placeholder of 1. And then that would give us 3x minus 2. We're looking like we're in good shape now. 3x minus 2 is one factor. Add the parts on the outside. X plus 1 is our other factor. And remember, these are both equal to 0. So now we apply what's called the zero product property. Set 3x minus 2 equal to 0 and set x plus 1 equal to 0. All right, for that first equation, I'm going to add 2 and then just divide by 3. So we get x equals 2/3 as one of our points of intersection for the x coordinate. For the other one, it's even faster. If I subtract 1, we get x equals -1. Whew, that's all step 2. All right, so step 3 and step 4 should go faster, I hope. Step 3, we need to now figure out what y equals. So what we need to do is take x equals 2/3 and plug it back in. Now, you could plug it back into either the quadratic or the linear. They should give you the same result. I like to plug it back into the linear just because it's faster. If x equals 2/3, then we would have 2 times 2/3 minus 3 is equal to y. The 2 is like 2 over 1, and we're just going to multiply straight across. 2 times 2 is 4, 1 times 3 is 3. But then we have to subtract 3. So again, another fraction. 4/3 minus 3 over 1 would be the same as 4/3 minus 9/3. When you have your common denominator, 4 minus 9 is -5, and then over 3. That's one y coordinate. I need just a little bit more space, so I'm going to shrink this screen a little bit so I can get my other value. All right, so now if x equals -1, we have to do the same thing. Plug it into that linear equation. 2 times -1 minus 3. This goes a little bit faster. -2 minus 3 is -5. Okay, one more thing. Now we write our answers finally as ordered pairs. In that first group over here, when x was positive 2/3, y was -5/3. And in the second group, when x was -1, y is equal to -5. That's solving algebraically, recognizing that -1, -5 would probably be pretty easy to find in a graph, but 2/3 and -5/3, algebraic isn't just another option, and it would be a little bit easier when it's not so easy to find your solution on the graph. We'll finish our notes for 2.7 tomorrow in class.